Okay, thanks all for coming. And thanks to PHP Southwest for hosting me again. I'm very pleased to be talking at my local meetup. And the talk I'm bringing tonight is called, the talk I'm bringing tonight is called Build Your Own Neural Network with PHP. So tonight, we are going to build an artificial neural network from scratch using good old PHP. First, just a few things about myself. My name is Vítor, and I'll be at the pub later tonight. So if we run out of time for questions, I know the schedule is quite tight. You can ask me at the pub, or if you prefer, you can send me a message on Twitter using my handle Noise Labs. Direct messages should be open. And now for a few disclaimers. So first, I don't know why you're laughing. I'm not an expert in this field, so I'm not using AI or machine learning in production, and as such, I won't be able to give you industry advice. I'm simply a student. Second one, there will be math throughout this talk, or to be more precise, oversimplified math. I hope it won't be too scary. It will make you leave the room. Just be a little patient on this. And third, there is a lot to cover in this talk. It's a complex topic, and I'll be going fairly quickly. But if something is not clear, please just raise your hand, and I'll try to clarify as we go. OK? So the reason why I'm giving this talk is because AI and machine learning is all the hype these days. I mean, AI is everywhere, and it's magic. I mean, you cannot go one day without hearing about machine learning in the news. It's just everywhere. And by the way, don't try this game because you would end up in a coma. Don't do it. Just don't do it. I mean, I think the only thing more hyped than AI is blockchain. But I won't be talking about blockchain tonight. But luckily for us, we have a talk from Fabien at PHP Day called Let's Create a Blockchain with PHP. So I think between ourselves, we got pretty much covered. So we should be good on the PHP side. So the second reason is, it's not often that we see PHP and machine learning together, which is sad. I think we deserve our fair share of AI and machine learning. And also, because if you're trying to learn a complex topic, such as machine learning, you might want to just focus on machine learning and pick a language that you're already comfortable with, so you can focus on machine learning. So that might be a good idea. So a couple of months ago, we have seen Google presenting its new digital assistant. So it's AI-based, and will make phone calls and appointments on your behalf, this AI agent. We are also seeing more and more driverless vehicles powered by AI. AI will soon be a doctor, and probably your lawyer as well, and maybe even the judge. And AI is also writing your code, or it will soon. This is a very interesting project where it uses machine learning to look at mockups, UI mockups, and it will write the front-end code for you. It's a very interesting article. The link is at the bottom. Please go and have a read. It's a very interesting article about machine learning. But AI is also responsible for this. So some folks thought it would be funny or a good idea to put Nicolas Cage in a bunch of films, such as Nicolas Cage, such as Indiana Jones, or Lord of the Rings. So this is all the good things that you can do with AI. And at the foundation of many of these applications, we have artificial neural networks. So this is what we are the answers that I will try to answer tonight. The questions that I will try to answer tonight. Why are they called neural networks? How do they learn? How can I write one using PHP? And finally, what the hell is deep learning? So the reason why they are called neural networks is because they are inspired by the human brain. So this is a brain. Well, half of a brain. And in a full brain, we have 86 billion neurons. And the neuron is something like this. It's a cell that receives, processes, and transmits electrical and chemical signals. So the signal is received on the dendrite. It is then processed within the nucleus and the cell body, and is then transmitted to other neurons through the axon. There is another way to look at this neuron, which will make more sense to us, maybe. So we can consider the dendrites to be our input. We can consider our nucleus to be performing some sort of activation function. And the signal flowing through the other neurons, through the axon, that will be our output. So the mathematical interpretation for this was first done in 1943, so it's quite old. That was our first artificial neuron, which was then revised in 1957, and that's called the perceptron, and that's closer to the model that I'm just about to show. So this is our mathematical interpretation for the neuron, for the biological neuron. So we have our input, and let's say, in this case, two previous neurons, or just an input. Let's say that we are going to call that x. Our input is going to be x. So x1 and x2. And then each connection from the input to the neuron will be affected by a weight, W1 and W2. And in the neuron, we're going to perform this operation. So the weight times the input plus a bias. That's B. So W and B is what we call the learnable parameters. So these are the things that our network is going to learn. So W will represent the connection between the neurons and the influence of one neuron on the next one. And B will be used to adjust the output signal from the neuron. So we can shift it left or right. So we then take the result from that operation, we pass it through an activation function, and then we have our output. That's the neuron output. I'm going to call it A. So this is what's happening inside a single neuron. So the equation for this, I'm going to call that variable Z, the neuron input, the weight times X, plus the bias term. It doesn't need to be just two inputs. It could be any given number of inputs. And the output will be just the result from the activation function. Okay? We pass in Z to activation function. That's our neuron output. And the activation function is basically modeling the firing rate, so the frequency of the spikes. And it's usually, on a neural network, on an artificial neural network, a non-linear function. And I'm going to explain why later, why being a non-linear activation function is important and matters for a neural network. So this is a very common activation function used for neural networks. It's called a sigmoid activation function. So for very big numbers, the output will be 1. And for very negative numbers, output will be 0. So It doesn't matter what input is going to be. The output is also going to be between 0 and 1. And that's our activation function, nonlinear. So if we take our single neuron and zoom out, we now know what's happening inside each of those neurons. So each neuron is represented by a circle, and this is our neural network. It's a feed-forward neural network. There are other architectures. This is the one that we are going to use tonight. It's a very common model where data will flow from the input layer all the way through the hidden layers until it reaches the output layer. Okay? To make it more clear, I'm going to use an example. So let's say you're going to build your cat classifier. So you want to build an application that, given a picture, it will tell you if it's of a cat or not. It's a very common example on the web. Well, cats are popular. So in this example, you're going to take a bunch of pictures. We'll take pictures of cats, and we're going to label that with a 1. A 1 for this is a cat. And then we're going to also take pictures of non-cats. It's a building, a person, a dog, a tree. That will be labeled with a 0. So that will be not a cat. Okay? And then we're going to feed our neural networks with those images. But first, we need to decompose that into pixels. So using RGB, I'm just adding those pixels, and I'm going to have one input per pixel. That's what I'm feeding to my network. This is what my network is going to receive. It will then be transmitted through the network, one neuron to the next one, until it reaches the very last output. Okay? And the output is it's just going to be a number. So in this case, it will make what we call a prediction. Given on that data, it will give us a prediction. So in this case, 0.73. And because it's closer to 1 than a 0, we can then say, OK, it's a cat. But ideally, it should be close to 1. It doesn't give us much confidence, 0.73. But that's the prediction. So what's happening here, I feed my network with a bunch of images labeled with a 1 or a 0, and somehow my network will learn that's a cat, or not. And this technique of feeding my network with label examples has a name, and it's called supervised machine learning. So this is the secret sauce behind our neural networks. So in supervised machine learning, what are we trying to do? We are trying to learn a function that maps our input, so those pixels, to a known output, a 0 or a 1. That's what it's trying to do, to learn that relation between inputs and output. So that when we see a new picture that it hasn't seen before, of a new cat it hasn't seen before, it can reliably make a prediction and say, OK, I think this is a cat. And that's the goal. And this is what's done in supervised machine learning. So machine learning is, this is a quote from Arthur Samuel, the field of study that gives us computers the ability to learn without being explicitly programmed. And basically what it means is there are no if statements. So the training approach in supervised machine learning is going to be, we're going to start with random weights and a fixed bias. We're then going to make a prediction based on that input data. I'm going to call it y hat. That will be our prediction. And y will be our known output, so the 0 or a 1. And then we're going to compare our prediction with what we know, which is going to be y, 0 or 1. Then we're going to adjust our network parameters, our learnable network parameters. That will be w and b, okay? And this is the learning part. This is what we are going to learn and adjust, the W and B, weight and bias. And then we're going to repeat this process until we get to a point where the prediction is very close to the output. That's what we want. So this is basically our algorithm for learning and for training. So this is a graph of the network error. The network error is the difference between prediction and the output. That's what error means. And as we start, the error is going to be very, very high, right? Because we are starting with random weights. The network will just make a random prediction. That's what's going to happen. That's on the very, very first step. And as we go, as we adjust our weight and bias, hopefully, if we are doing things right, we're going to see the error drop until it goes below a threshold that we define. Once it goes below that threshold, we just say, I'm happy with this, stop the training, stop the learning process, I'm going to use my network. There is also a number of iterations, and I can define a maximum number of iterations in case I don't want to run this forever, in case it goes bad. It happens frequently. So this is my very basic network with a single neuron. This is the most basic I can get. But I can use my very basic network to solve a problem like this. So let's say that we have the salary, our input x-axis, that will be our salary. And then we'll have the rating, satisfaction rating, associated with that salary. So we're collecting this information from employees. And kind of a predictable, very high salaries have a very high satisfaction rating. No surprises there. And our very simple network will be able to learn something like this. It will be able to learn this function. Okay? After training, it will learn this function. It doesn't seem too complex. So that when we get a new value of the salary, it hasn't seen this value before, so let's say 50K, then it will tell us that the satisfaction rating will be around 70%. That will be the prediction. Now, this example is nice and easy, but it is no challenge for a neural network. We need something more complex. This is way too easy. I'm going to give you the XOR. Just to refresh on the XOR, equal input 0, 0 and 1, 1 will have an output, a known output of 0, and different inputs, 0, 1 and 1, 0, will be 1. And this is what we're trying to solve tonight. It's a complex problem. So if I put this on a graph, we have our zeros in red, and we have our ones, the triangles, in blue. And if we try to use our neural network to solve this problem, our single neuron network, this is the best it can do. And as you can see, it doesn't solve our problem. And the reason why is because it's not linearly separable. There is no way with a single neuron that I can separate my zeros from my ones. And that's why the XOR is an interesting problem, and apparently a complex one. To solve this, I need to upgrade my very simple neural network to something like this. I'm now adding a hidden layer. We still have one output, but now I'm adding one hidden layer with 2 hidden neurons. And because this is a feed forward, you can see the relations between our input and our hidden neurons to the output. So the reason, that's why I was talking about nonlinear activation functions, is because if we are using a nonlinear activation function, then a 2-layer, or even bigger, but at least a 2-layer hidden network can be proven to be a universal function approximator, which means it can represent any function, theoretically. there are some issues. But because of this, and also because they are computationally efficient, actually, this is what makes them so powerful. And that's why it's a good idea to use, and that's why they are so popular these days. So this is the neural network that we're going to use tonight. And this is the neural network that I'm going to use to solve our XOR problem. So with all this information, we are now ready to start coding our neural network. Guys, still following? Too fast? It will get worse. So all the code that I'm going to show is in this repo. So don't worry if you miss some of the details in the slides. You can check out this code, have a play with it, see how it works. So I'm going to start with my basics. I'm going to write my neural network class, and it's going to have two methods. One, train. So I need to train my network. It'll have inputs and output. And then a method to make a prediction. So I can give you a new value or some of the already existing values in the input, and it will give us a prediction. And hopefully, it will be something close, something good. So for the XOR, these are my inputs. And the target is the corresponding target for each one of those inputs. Okay? And I just instantiate my neural network class. It's doing nothing at the moment. That's our very, very, very first step. So I'm going to start with a network topology. And you have seen this before. We have two inputs. We have two hidden neurons and two layers. This is a bit of confusing, but we have hidden layer and the output layer. The input layer doesn't count as a layer. It's just standard notation. I know it's confusing. It's just the way it is. And we're going to have one output. So that's our network topology. And now for the parameters. So if you remember from the single neuron, we're going to have W, B, the weight and bias, and then the neuron input is going to be Z, and the output, the neuron output, is going to be A. I'm going to put this in another class just to make the code cleaner. I could put it in the neural network. And then I'm just going to set that in my neural network construct. No need for dependency injection. This is good enough. Now, I could be using nested arrays and just doing a bunch of for each and for loops to make the multiplications between the weights and the inputs, and that will be absolutely horrendous. Luckily for us, there is a better data structure, which is a matrix. I hope you still remember the matrix from your algebra classes. So with a matrix, it's much cleaner. I'm going to store in the first row of the matrix connections coming to my first hidden neuron, okay, and my connections coming into my second hidden neuron. It will be my second row, and then the bias is just one for each. It's also makes it really easy to read. And for the output layer is even easier. Just two incoming connections to my single neuron, just one row, and the bias will be stored in my second matrix. Okay. I'm not going to roll my own matrix data structure. I'm going to use something that already exists. Luckily, PHP already have these libraries you can already use. I'm going to use math.php. Actually, there is a library called mathml, I think, for machine learning. So it gives you also a bunch of machine learning related tasks. But for this, I just need my matrix. So I'm going to use math.php. And in math.php, the way to create a matrix, you pass in a bunch of an array of arrays, one for the row. And then I can use a helper class, matrix factory, to create my matrices, A and B. And then I can do operations. I can add and subtract. I can multiply two matrices. And the Hadamard product will give us an element-wise multiplication, which is a slightly different multiplication. And finally, I can run a function against each element of the matrix, and this is going to be quite useful, as you're going to see later. So, other programming languages such as Python and other libraries such as NumPy, they use something called vectorization. And vectorization is just a very efficient way to do matrix operations, just multiplication with very, very, very large matrices. And that's why PHP has a handicap in machine learning, because to the best of my knowledge, PHP doesn't have the support for vectorization. That's why Python might be preferred for machine learning. But I found this library. It's quite new. It's like 2 or 3 months old, and it gave us an array data structure written in C that can also be used to perform matrix operations. So this could be the performance boost that PHP was in need. So check out this project. It seems promising. I'm not going to use it. It will just make things even more complex. But please have a look at this. Might be something really interesting. So now I'm going to write my first building block, the activation function. Okay. Just a reminder, I'm going to use the sigmoid function. And the equation, the formula for sigmoid is just this one. So I just need to code this little formula. So I'm going to write my sigmoid class, okay? And there are more activation functions. I'm just going to pick this one. It's very, very standard one. And I'm just going to implement my sigmoid method. And then in compute, I can compute the sigmoid for a full matrix. What I'm going to do, I'm going to each element in the matrix, just calling sigmoid. And that's it. Then I have my matrix back. So that's my sigmoid function. And I just set it in my neural network. Just because we could replace it with something else. But for now, I'm just going to use the sigmoid. And with this building block, we're now ready to start writing the code that trains our neural network. So this is the algorithm for training. Okay? I'm going to initialize my network. I'm going to initialize the weights and bias. That will be my first step. I just need to do it once. And then I'm going to write a loop. So until the error doesn't go below my threshold, which is max error, I want my network to keep training, or until it reaches a number of iterations, a big number of iterations. And for each of the training examples, and training examples in this case is those 4 examples in the XOR, you know, the 0, 0, 0, 1, that's my 4 examples. In the cat example, it could be one of the pictures that we are feeding the network. So we're going to look through those training examples, and then I'm going to perform these 4 steps. Okay, first it will do a forward pass. It will go from the input all the way to the output. Then I'm going to compute the cost. Compute the cost means the error. Okay, between the prediction and the real output, that's the cost. Then I'm going to do something called backpropagation. And this is the magic behind the learning process. And finally, I'm going to adjust the weights and the bias. And then I keep repeating this until my error, hopefully, will go below my threshold. Because sometimes neural networks are stubborn and they just decide that they won't go below my error. So the first step will be initialize parameters. And what are we going to do? The B matrix, I just set it to 0. So all elements in the B matrix is going to be 0, okay? And that's the dimension. It's always 1 for the number of columns. It's row column. And for my weight matrix, I'll also start with 0, and then I'm going to set a random number between 0 and 1. That's what the value I'm going to assign to the weights initially. Just because 0 and 1 is a very standard range for initializing the weights. It's very common. There are more advanced techniques, but for us this is simple enough, and it will work. And for the output layer, basically the same. Initializing my bias, initializing my weight matrix, random number between 0 and 1. And this is my initialize parameter step. And because I'm only going to do it once I create my neural network, in the construct, I just call that, so I have it initialized. And once calling that, I get something like this. Okay? So weights and weights all between 0 and 1, just random values, bias, zeros. This is what it looks like before I start training. So now I can go to my train method, and the first thing I'm going to do, I'm just going to convert my arrays into a matrix inside, because I'm going to use matrices inside my neural network class for everything. So I just do that conversion. And then I'll also set my maximum number of steps to be 20,000. It's a reasonable value. Seems too high, but it actually takes a lot of steps to converge. And then I'm going to set my max error to be 0.01. For me, this is good enough. And the initial error is just going to be infinite. Okay, so this is what I've just shown in my previous slide about algorithm for training. It's just our two loops together. So now I'm going to implement those 4 steps that you have seen there. So the first step in there, it's a forward propagation pass. And for this, I'm going to use these 2 formulas. If you remember the single neuron, it's exactly the same thing. The only difference, by the way, I'm using capitals because now we are using matrices, just a notation. So the A is the output from the previous layer. So the subscript L is just tell us in which layer we are. It goes from 1. So for this example, we have 1 and 2, which means that for the hidden layer, because there is no previous layer, it's just going to be X. And for output layer, it's going to be the A1 is going to be the output from the hidden layer. Okay? And then the second step is calculate the output, which is so that's the sigma symbol, and that just means I'm applying the sigmoid function to my previous to the neural input. So this is the forward pass. This is the equations I'm going to apply. So now I can write my do forward propagation method. This is just a trick. I'm just setting inputs to be my layer 0, just to help me do this multiplications. And then I'm just going through all the layers. I'm just using 2. I could be using 3, 4. It's just basically a for loop. And in the first step, I'm just going to calculate Z, just doing our matrix functions. So multiply and add the bias. And then I'm just going to get the result from my activation function, which is the sigmoid, and store it in A. So those are the 2 steps. I get Z and I get A. And if I return the last value, so the last A is going to be the output from a network. And that actually is our prediction. So if I feed input data, the last value, the last output is actually the prediction that the network has made. Okay, so that's what I'm returning. Do forward propagation, in fact, returns a prediction. So that will be my first step. So now, if I feed it with 0, okay, our first example would be 0, 0, and with those weights, it just makes a prediction of 0.61, which is a terrible prediction. But we'll make it better. So now I'm going to compute the cost, or the network error. And for that, I need to pick a function. And in this case, I'm going to choose the mean square error. It's a very simple cost function, but also very commonly used. And because we have one single output, it's just that example below. I mean, it's just output minus the prediction squared, and that's it. So if I implement this, it's basically subtract 2 matrices and square it, and that's it. And that's my compute method on my mean square error class. So I can now just set it in my. So if I look at my network, I can see that the prediction was 0.61. It should be 0, so the error is actually 0.38. So it's quite high. It's quite big error. So now I can set that as my second parameter in my neural network. So now I have my activation function. I have my cost function. It's getting there. So for the compute cost, I just call my method on the cost function and add it to my loop. And that's my second step. I'm going to store the errors in that costs array because it's actually, I'm going to do that for 4 examples. Okay, so I need to store those 4 times in my costs array. So now we have backpropagation. And backpropagation is the most complicated bit. Any questions so far? All clear? I believe you. Well, I don't. So backpropagation is different. It's a supervised learning method that we use for feed-forward. So remember, we are seeing a feed-forward network today. And what it's going to do, it's a bit different because our starting point will be the end. We have gone from the input to the output, and now we're going from the output to the input. So what we're trying to achieve with backpropagation is to look at each individual weight in the network and see how much it contributes to the error, to the final error, so that we can adjust individual weights. So that's why we start from the error, from the end, and we go through each weight all the way back to the beginning and see if I change this weight, how much does the error changes. And backpropagation relies on something called gradients and derivatives. And I'm not sure if that's something that you still remember. You may want to forget it. But basically, a derivative will give us, so if you change slightly your input, you can see how much the output changes. So that's why we're trying to achieve, that's why we use derivatives. And the process of finding the derivative is called differentiation. So that's why my method is going to be called something like differentiate. Okay. And gradient is just a multivariable generalization of the term derivative. So it's basically the same thing. These are the equations that I'm going to use for my backpropagation step. I'm not going to explain how we got there because that's like topic for another talk. You just have to believe me. So we are going to start. Remember, we're going to start at the end, output layer, and we're going to start with D for. I'm going to use D for gradient or derivative. That's why I'm calling that. And it will start by using the derivative of the loss function, the mean of square error. That will be my first step. And then I can calculate dz by just using the previous value, element-wise with the derivative of the sigmoid function. And then I can calculate dw using dz times a. By the way, t is for transpose. It's just a way to rotate the matrix so I can do matrix operations. Don't worry too much about it. And db is just equal dz. And the thing that we are interested with is dw and db, okay? da, dz, just temporary variables. That's the stuff that we want. dw and db, that's what matters. And for the hidden layer, it's basically the same thing. The only difference is the EA, okay? Is that in output layer, we start with a derivative for loss function. For the hidden layer, it's just w times dz. So this is what we're going to implement. That's the backpropagation step. So I'm just going to add 2 new variables, dw and db, just to store that. And now we have to actually calculate the derivatives for the cost function that we use. So the derivative is quite easy. It's just 2 times output minus the prediction. Very simple. So that's what I'm going to implement in the differentiate method. Okay. And the same goes for the sigmoid derivative, for the derivative for the activation function. It's just the sigmoid times 1 minus the sigmoid. So implementing that is, again, very easy. Sigmoid times 1 minus the sigmoid. That's what I'm going to implement. So each one of my classes is going to have a compute for the forward pass and a differentiate for the back pass. I need 2 methods in each. It seems like a bunch of code, but basically what I'm doing is implement this first step. Okay, here for the output layer. It's just because it's special. We start with a derivative for the cost function. Then we calculate dz, dw, and db. And the same goes for the hidden layer. So all hidden layers I'll calculate in the same way. So I just calculate da, dz, and I store my information in dw and db. So I want to keep that. The rest I can throw away. That's why there is no result being stored from the backpropagation step. It's already stored in our parameters, dw and db. That's what I'll need to keep. So my last step is the update parameters. And for that, I'm going to use something called gradient descent. And the formula is this. I take the current w, and I adjust it slightly by taking that quantity, which is alpha times dw. And for b, I'm going to subtract it with alpha times db, like we just seen before. And the learning rate, which is the term alpha, will control the jump between, it will control how much I adjust dw and db. And there is a trade-off. We cannot go too small on the learning rate value or too big. If it's too small, it will take a long time. If it's too big, I might just fail entirely. So if we look at the graph, that's the cost decreasing. I want to stay there. I don't want to miss that sweet spot. And so that's my value of w that I want to find. Okay. So adjusting the learning rate, sometimes it's an empirical process. I'm going to set it to be 0.1, which is a very classic value used for the learning rate. And then update parameters is simply adjusting my new w and adjusting my new b, just using the formulas we have seen before, with learning rate being updated. You can then change the learning rate to be smaller or higher if it fails to converge. That's something that you can adjust. So that's my last step. I just take the total cost for each of those 4 examples and do an average, and that's my error. So the full code for the training step is this one. And this is all I need to train my neural network. It's all there. Doesn't look too bad. Even, yeah. It's not the end. It is the end for training. But now I'm going to use it for something useful, which is making predictions. So we train it so that it can make predictions. And I'm going to cheat here, because usually we would send a new value, but we can also use the values that it has seen before just to confirm that it has learned properly. So to make a prediction, I just need to call do forward propagation again. Because remember, the result from this is just a prediction. So that's the only thing I need to use. I'm just going to reuse it. So if I run my XOR example, I start with very high error. Remember, random weights at the beginning, very high error. And as it keeps going, error is going, decreasing, hopefully, until it stops at 0.001, because I've set my error to be 0.001. Once it got there, it stops training, and it's good enough, hopefully. So now I can call it, and with a target of 0, I got 0.03, quite close. That's good. That's success. For 1, I get 0.96. Again, that's very good. It's very close to what I want. And the same for the 1, 0. And the same for the last line. So it's 0. It's very, very close. So it has learned properly how to recognize an XOR. And that's good. I mean, this is success. We are in World Cups season, so I thought it was appropriate. So recap, we are almost at the end. Neural networks are inspired by the human brain. And today we saw a feed-forward net. There are other architectures, and actually for the images, just don't use this one for the cat classifier. There are better architectures. It uses supervised machine learning, which basically means learn from examples. And the error is minimized using those two techniques, backpropagation and gradient descent, where they just use clever derivatives to calculate those errors. And finally, neural nets can approximate any function, and that's what it makes them so powerful. So just one little thing. This is the net that we've seen today. But if you're trying to learn something more complex, you can add more hidden layers. And you don't need to stop there. You can add even more hidden layers. And if you add enough hidden layers, then you can call it deep learning. And that's my last slide.
Thanks very much. That's amazing talk.
Please give feedback. That will be very, very helpful.
Please give feedback. We've got about yeah, we've got one quick question. We've got a quick question. Anyone? One quick question there.
Yeah.
Is that heavily based on graph theory then?
On graph theory.
Yeah, use weights for the inputs and the outputs. So I'm assuming graph theory has quite a huge role to play in that.
I'm not entirely sure on that one because it's not a cyclic graph. It's just one way.
So
they don't create graph. Yeah.
Data structures. Sorry, I had a data structure.
Probably not because they rely actually on the backpropagation technique. Okay. But there are maybe Boltzmann machines are using graphs. I'm not sure about feed-forward neural nets.
You will be
the inputs that you gave, the zeros and ones in the last one, the prediction, we have to give zeros and ones as input before you give it all the numbers as well.
Oh, you can give any number. Yeah. Just be consistent. Actually, it could be -1 and 1.
Okay.
But then the activation function could be different because then you want something between 1 and -1. Thank you.